Alright, so these are going to be your lecture notes for exponentials and logarithms. Now, if you're in the trigonometry class, this entire video will be for you. If you are in the Algebra 2 class, you'll specifically need to be focusing in on 10.1, 10.2, and 10.5, as well as the videos for graphing logarithms at the end of your packet. But of course, it doesn't hurt to listen in, especially on this first part of the video, where we're going to be talking about 5.1, properties of exponents, so a throwback to Algebra 1. In example 1 here, we have this quantity of 3x cubed y squared times negative 4x squared y to the fourth. So first off, I'm going to notice that I can multiply the 3 and the negative 4, getting me a negative 12. The next thing that I can multiply is x to the third by x squared. And when I am multiplying, I'm actually going to add their exponents, getting me x to the fifth. Lastly, I have y squared times y to the fourth. Once again, I'm going to add their exponents, and we have 2 plus 4 getting me 6. So my final answer, voila. Alright, so next we have some division happening, and when we are dividing things that have a same base, we are going to subtract their exponents. So we're really going to subtract 8 from 3, getting me p to the negative fifth. Now, we're not allowed to have negative exponents, so we are going to flip its location and give it a positive exponent, now getting me 1 over p to the fifth. Whenever I raise a power to a power, I'm actually going to multiply their exponents. So 3 times 5, getting me a to the 15th. Whenever I have many things in a quantity being raised to a power, I need to remember that everything is going to get an exponent, okay? So here, negative 2 to the fifth power, I have p to the third to the fifth power, and I also have s squared to the fifth power here. So negative 2 to the fifth power, that's going to get me negative 32. P to the third to the fifth is going to get me p to the 15th. S squared to the fifth is going to get me s to the 10th, and ta-da, there's my final answer. Alright, once again, I'm going to give everybody in this next quantity an exponent of 4. And I'm just going to write it all out. The only thing I need to really simplify is this negative third to the fourth power. So negative 3 to the fourth power, that's going to get me a quantity of 81. So I have 81 times x to the fourth over y to the fourth. Once again, for the last one, I'm going to give everything their negative 3 exponent, but I'm going to remember the fact that we cannot have negative exponents, so I'm going to flip their location, giving them positive exponents. Now 4 to the third power, I'm going to simplify. 4 to the third is going to be 64. So we have 64 divided by a to the third. Let's combine a whole lot of these happening at once. One thing I can do to make my life a little bit easier is first work inside my parentheses and see if there's anything to simplify. Notice that we have an x to the 3n divided by an x to the 2n. Division means subtraction of exponents. So we really have x to the power of 3n minus 2n, which gets me x to the nth power, which is going to be in our numerator. So now I have less to deal with. I'm going to give everything an exponent of, I'm going to give everything an exponent of 4. So now I'm going to distribute in here. And remember, when I raise a power to a power, I multiply their exponents. So in my denominator, I have y to the 12th because he was to the third, and I multiplied it by 4. Now, lastly, all I got to worry about is this negative 2, that quantity. Maybe I should put that in parentheses. Negative 2 to the fourth power. Well, that's really the same as 4 squared if you didn't know. Just a little side note. That's going to get me the quantity of 16. So I'm going to rewrite that, give myself a 16, and we have our final answer. Alright, so that's 5.1. Now we're going to get started with 10.1. Alright, so I'm going to make an XY table for my graphing, and it's just going to make my life a little bit easier. It's kind of good old reliable, so you're going to have to forgive me when I go to actually plot these points. I'm going to start out at negative 2, and I'm going to work my way all up to positive 2. First off, 2 to the negative second power, that's equal to 1/4. 2 to the negative first power is equal to 1/2. 2 to the 0th power is equal to 1. 2 to the first is equal to 2, and 2 squared is equal to 4. Now let's carefully plot these. Maybe it'll help if I zoom in a little bit, make my screen a little bit larger here. All right, so first off, 2 to the 0th power gave me a y value of 1. 2 to the 1st power gave me a y value of 2. 2 squared is 4, a little bit there. And it started getting smaller and smaller and getting really, really close to the line where y is equal to 0. And what that creates is actually going to be called my horizontal asymptote. I cannot actually touch this line. If you noticed, I just kept getting really small. Nothing was ever getting negative, nothing was ever getting 0, it was just getting really small. Alright, so that means our domain, there is not a single x value that I'm not allowed to plug in. However, for my range, I must be bigger than 0. Alright, well, let's take a look at when we have exponential growth and exponential decay. We're really going to be focusing in on the b value here, our growth rate. And if it's between 0 and 1, like my first one here of 1/5, we're going to have exponential decay. Things are going to be getting really, really small. Whenever I have a b value that's greater than 1, like 4, I'm going to have growth. Now what about like c, 1.2? Even though it's slightly bigger than 1, it's still going to give me growth. It's slightly going to grow a little bit faster than anything else. Alright, continuing on with section 1, we're now going to write an equation. Notice in this problem, it actually is going to give us a starting value. In 1983, there was 102,000 farms. This is going to be our value for A in our exponential equation. In 1998, well, that's 15 years from the start. We dropped down to only 80,000 farms. We are going to use these two coordinates to figure out what our growth rate is, our b value, because that's the only information we don't know. So first off, we're going to use our value of 15 for our x and 80,000 for our y. 102,000, that's going to be our value for a. So let's just plug in our information. 80,000 is equal to 102,000 times the value of b that we don't know, raised to the 15th power. So first off, I'm going to divide both sides by 102,000. That's going to get me 0.78 is equal to b to the power of 15. Now I want to get rid of an exponent of 15, so I'm actually going to take the 15th root of both sides. The 15th root of 0.78 is going to get me 0.98 approximately, and this will be our value for b. So now we have our entire equation. Y equals our starting value of 102,000 times 0.98 raised to the x power. Notice how my b value is exponential decay, which makes sense because we are decreasing the amount of farms. Why don't you try b? Notice that we're doing 2010, so try to figure out what is our value for x in this scenario. Alright, example 4, we got to remember those properties of exponents. Whenever I am multiplying, remember that I'm going to add my exponents. So we also need to remember the fact that we cannot combine these two radicals because they do not have the same radicand. Whenever I raise a power to a power, I'm going to multiply my radicals. Radical 2 times radical 3 is going to get me the square root of 6. Whenever we're solving equations, exponential equations, one of our goals is to be getting the same base. So notice on my left-hand side, I have 3 to the power of 2n plus 1. So I'm going to ask myself, 81, can I rewrite him as having a base of 3? 3 to what power? 3 to the 4th power. So now, if we think about it logically, 3 to a power equals 3 to another power, we can set their exponents equal to each other and solve for our variable. So now, we're going to have n equals 3 halves. Now what about in b? 4 to the 2x equals 8 to the x minus 1. 8 cannot be represented as 4 to any power, so we actually need to rewrite both of them. 2 to the 2nd power is 4, and 2 to the 3rd power is 8. Whenever I raise a power to a power, I'm going to multiply their exponents. And over here, I need to remember that I'm multiplying by the whole quantity of x minus 1. So we now have this expression, where we can set their exponents equal to one another. So 4x equals 3x minus 3. We solve for our variable, and we get that x is equal to negative 3. All right, we're now taking a look at 10(2). First aspect we're looking at is converting between logarithmic to exponential form. And I kind of look at it as a snail. I'm going to take the base of my logarithm, I'm going to raise it to the power, and then set equal to what's in the inside. Here's my little snail right here. So we have 8 to the 0th power is equal to 1, which mathematically is true. So 2 to the power of negative 4 is equal to 1/16. Again, mathematically true. Now let's go in reverse and let's make an observation. Notice that the base of my logarithm also was the base of my exponential form. So 10 is a base here, so he's going to be the base of my logarithm, which isn't necessary because all logarithms are assumed to be base 10. Alright, notice that whatever the logarithm was set equal to became the exponent inside our exponential. Therefore, whatever our exponential was equal to is on the inside of our logarithm. So log base 10 of 1,000 is equal to 3. Let's snail it out just to see if it worked. 10 to the third equals 1,000. Ta-da! How about this one? Log base 9. Okay. So log base 9, the exponent is going to be what it's set equal to, and whatever the exponential is equal to is on the inside of my logarithm. So let's check to see if it worked. 9 to the power of 1/2 is 3. Very good. All right, let's evaluate a logarithm statement because we don't need a calculator for this. Log base 2 of 64. Well, let's just set this equal to y. Let's also unravel it. 2 to the power of y is equal to 64. So 2 to some power is equal to 64. What is that power? Well, that's going to be 6. 2 to the 6 is 64. Now, exponentials and logarithms are handy because they are inverses of one another. So if I have log base 6 of 6 to the 8th power, it's essentially going to cancel out, leaving me with my exponent of 8. Just like this guy over here, 3 to the power of log base 3 is going to leave me with whatever was on the inside of my log, because they're inverses. Alright, let's finish up 10(2), where we're solving a logarithmic equation. And one way to look at it is reading this as 4 to the power of 5/2 is equal to n. So 4 to the 5/2 is equal to n. And if you'd like, you can always type this into your calculator, or you can use the properties set forth in your textbook, whatever makes you most comfortable. Regardless, you're going to get that n is equal to 32. Alright, we're now taking a look at 10(3), using properties of logarithms. If I'm given log base 2 of 3, and I need to somehow use it for log base 2 of 48, I need to figure out how they're connected. Well, 48, like the textbook says, that's really going to be 3 times 2 to the 4th power. So I can really break this into log base 2 of 3 times 2 to the 4th power. Okay, well, multiplication within logarithms really means addition. So I have log base 2 of 3 plus log base 2 of 2 to the 4th power. Well, we know that log base 2 of 2 to any power is just going to leave us with our exponent, and we were given this information in the problem. So we're really going to have 1.58, there's my decimal, 5 plus 4. Alright, what about this one over here? Log base 3 of 5 is equal to a quantity, and log base 3 of 20 is equal to another quantity. Somehow they're connected to log base 3 of 4. Well, observe that 20 divided by 5 is equal to 4. So we really have log base 3 of 20 divided by 5. Well, division actually means subtraction. So I really have log base 3 of 20 minus log base 3 of 5. Once again, I can take the values that were given to me in the problem and substitute them in. So we really have 2.7268 minus 1.465. Alright, so now we're taking a look at this real world problem here. We're dealing with loudness of a person versus the loudness of 10 people, okay? So first off, let's look at the loudness of one person. That's where we get L1. We're going to use this formula here, 10 times log base 10 of R, where R is that sound's relative intensity, Okay, well, the problem gave to us that the relative intensity of one person is just going to be 10 to the 6th, okay? Well, we can assume that the level of intensity for 10 people would just be 10 times that amount. So for level or loudness 2, where we have 10 people, we're going to use that same formula, but on the inside, we're going to have 10 times 10 to the 6th, okay? So now, to figure out the difference between these, we're going to subtract them. So we're going to take 10 times log base 10 of, you can really say 10 to the 7th, because 10 times 10 to the 6th is 10 to the 7th. And I'm going to subtract 10 log base 10 of 10 to the 6th. Okay? Well, now I can just use my properties, okay, if you notice. But first off, let's factor out a 10 from both of these, getting me log base 10 of 10 to the 7th minus log base 10 of 10 to the 6th. Notice that 10 was essentially their greatest common factor. Well, on the inside, subtraction actually condenses into division. 10 to the 7th divided by 10 to the 6th. Well, 10 to the 7th divided by 10 to the 6th is just 10. And the log base of 10 isn't just going to be, it's just going to be 1. It's inverse property. So we really have 10 times 1, which is just 10. All right, so let's continue using our properties here. We're given log base 4 of 6, and we need to use it somehow to find log base 4 of 36. Well, 36 is really just going to be 6 squared. Okay, so we're really dealing with log base 4 of 6 squared. Well, exponents can be brought out to the front and turn into coefficients. So we really have 2 times log base 4 of 6. Well, the question gave us this value that we can substitute in for log base 4 of 6. So we really just have 2 times the quantity of 1.2925. All right, let's solve some equations here. Subtraction. I'm knowing that I'm going to have to do some division, but the first thing I can do is bring the 3 in as an exponent. So we're going to really have log base 5 of x to the 3rd divided by 4 is equal to log base 5 of 16. Well, the log of a quantity is equal to log of another quantity, so I can just set their insides equal to one another. Okay? Next, I'm going to multiply both sides by 4, so we have x to the 3rd is equal to 64. And now I'm going to take the 3rd root of both sides, and I get that x is equal to 4. All right, what about the condensing of this one? Addition means multiplication. So I really have log base 4 of the quantity x squared minus 6x equals 2. Well, I can now use my little turning it into exponential form. 4 squared is equal to that quantity. So we get x squared minus 6x is equal to, well, 4 to the 2nd power is going to be 16. Well, now this is turned into the quadratic. So I'm going to subtract that 16 from over there, and it's set equal to 0. So now I'm going to ask that you please solve your quadratic, get your quadratic thinking caps on, and check your answer with the textbook. All right, so example 1, I'm just going to ask that you learn how to type logarithms into your calculator and check your answer with the textbook. Example 2, we have an equation. Log of E is equal to 11.8 plus 1.5m, and we're given an m of 8.5. So on the right-hand side of my equation, I'm just going to start simplifying. 11.8 plus 1.5 times 8.5 is equal to 24.55. To get rid of a logarithm, we need to focus on what is the base of that log. Well, all common logs have a base of 10. So what I'm going to do is I'm going to take 10 to the power of on both sides. 10 to the power of. I'm essentially giving them a base of their exponent of 10. So we really have 10 to the power of 24.55, which your textbook will put into scientific notation of 3.55 times 10 to the 24th power. All right, what about this scenario here? In the previous section of 10.1, we were able to get things to have the same base. Well, 3 and 11 will never have the same base. So what I need to do to get my exponent brought down front is take the log of both sides. When I take the log of both sides, I end up with x times the log of 3 is equal to the log of 11. Lastly, I'm going to divide both sides by log of 3, and x is going to be equal to log of 11 over log of 3. Now this is going to be a decimal. You need to type it into your calculator. You're going to approximately 2.1828. All right, what we essentially just did there was called the change of base formula. The change of base formula is a way of rewriting things in terms of having the common base logarithm of 10. So log base 4 of 25 is really going to be rewritten as log of 25 divided by log of 4. This is especially helpful if you don't have an updated calculator. Just like before, we're going to do 10-5, but I want you to do the first example on your own. Make sure you know how to find the button E on your calculator. Make sure you also know how to find the button LN, natural logarithm, on your calculator. Alright, so we're going to take a look at converting again. Let's actually start with B. You need to remember that ln, that's just another way of me saying the log base E of something. Log base E of x is equal to this decimal here. Okay, so we're going to just snail it. E to the power of 0.6931 is equal to x. So here is my converted expression. Okay, so now let's use that logic on the other one. Notice that the quantity that is in the exponent is what I'm going to be set equal to. Okay, I'm going to take the natural log regardless. That's just going to be log base E. And whatever that the exponential form was set equal to is going to go on the inside of my logarithm. So we have the natural log of 5 is equal to x. Alright, let's use that inverse property again. Because E and the natural log are inverses of one another, we are just going to be left with 7. Once again here, because they are the inverses of one another, I'm going to be just left with 4x plus 3. Gotta love that inverse property. Alright, so now let's use our inverse properties to help us solve an equation. First off, I need to isolate my e, so I'm going to add 7 onto both sides. So we have 5e to the negative x equals 9. Divide both sides. E to the negative x is equal to 9/5. To get rid of an e base, I'm actually going to take the natural log of both sides. So negative x is going to be equal to the natural log of 9/5. And lastly, I'll divide both sides by negative 1. So this is something I'm going to type into my calculator, and I'm going to get approximately negative 0.5878. Make sure you also can type this into your calculator here. Alright, what about this very last one? Solve. Natural log of 5x equals 4. Well, everything's already isolated that I needed to have isolated, so all I need to do is get rid of this natural log. Well, the opposite of natural log is e. So I'm going to give everything e to the power of, e to the power of. So 5x is equal to e to the 4th power. Divide both sides by 5. So x is equal to e to the 4th over 5. Type that into your calculator. You can get approximately 10.9196. Alright, we're now going to take a look at the last section, section 6 of chapter 10. Well, we're dealing with some real-world problems. The first one that we're going to deal with has our rate of decay equation here. Same things apply. A is still going to represent that initial amount. In this particular problem, our initial amount is 130 milligrams of caffeine. Okay? So then the question is asking us for the length of time it'll take for half of it to be eliminated. Okay? So we don't know the value for x, but we do know that half will be left, and that'll be 65. So we're going to plug in information that we do know. We also know that we have a rate of 11%. Now we don't use percent, so we're going to convert that into a decimal of 0.11. Okay? Alright, so let's use this as our y. So 65 is equal to a value of 130. We're going to do 1 minus 0.11 because remember, that value for b, if we are decaying, it needs to be less than 1. Raised to the power of t, that x value that we do not know. Okay? Alright, so we're going to divide both sides by 130. We get 0.5 is equal to 0.89 to the t power. Okay? All right, so now we're going to take the logarithm of both sides. That'll bring down our t. So then we're going to have log of 1/2 is equal to t times log of 0.89. Divide both sides by log of 0.89. So then we have something that we need to type into the calculator. Log of 1/2 divided by log of 0.89 is equal to our value for t. Type that in, we get approximately 5.948. So what this means in the context of a real-world problem is it's going to take about 6 hours for half of this caffeine to be eliminated from a person's body. Alright, so the next form of an equation we're going to use is of the form y equals a times e to the negative kt. This will typically be used when dealing with radioactive decay. Scientists actually use this formula. Alright, so in this problem, we actually don't know our value for a, and we're just looking to solve for k, okay? Specifically, we're looking for the situation of half-life. So we're going to set our equation equal to 1/2 of our initial amount, a. That's going to be equal to a times e to the negative k. Now the t that was provided was 5,760. Okay? I'm going to divide both sides by a, so we get 1/2 is equal to e to the negative k times 5,060. To get rid of an e, I'm going to take the natural log of both sides. So the natural log of 1/2 is equal to negative k times 5,760. I'm going to divide both sides by negative 5,760, so that we get that k is approximately 0.00012. Alright, so then in the next problem, we're actually going to plug in the information that we are provided, okay? Once again, we still don't have an a. This is going to be this general situation, okay? But we're going to be looking specifically for 3% of the initial amount, so 0.03 of our initial amount, a, okay? Once again, it's okay that we don't know what a is. But we do now have our constant k, so negative 0.00012. Now the time that we're given, we don't know. That's actually what we're solving for. We're trying to figure out when did the mammoth die. Okay, so we divide both sides by a. 0.03 is equal to e to the negative 0.00012t. We're going to take the natural log of both sides. So we have the natural log of 0.03 is equal to negative 0.0012 and t. Divide both sides by negative 0.00012. And we're going to type this whole expression into our calculator and find that t is about 29,221. So that was a long time ago that the mammoths died. Alright, looking at example 3, we're now looking at exponential growth. Once again, in the problem, I'm given a value for a, which is my starting population. I'm given my rate of 1.5, which will convert to 0.015 as my r. And we're given our time because it's going to be the difference between 1910 and 2010. So 100 years. That's what I'm trying to figure out what the population is. So I'm going to plug in all the information that I've already been provided. 1 plus my rate. Notice that we want our b value to be bigger than 1 because we are growing. And our value for t will be 100 because there's going to be 100 years. So this is actually just an expression that we'll type into the calculator. And we get that y is equal to 531,845. Okay, there's our population. The very last example actually deals with inequalities, but I do want you to take a look at it because it deals with another growth equation here, okay? So we have an equation of the form y equals a times e to the kt, okay? And we're actually given the equations for these two countries, and we're trying to figure out when is India going to be bigger than China's? So essentially, when is this equation here going to exceed my other equation here? Okay? Alright, so The approach that your textbook takes is taking the natural log, actually, of both of these quantities here. And notice that between our a value and e, we actually have multiplication. So you can actually break this into the natural log of 1.01 plus the natural log of e to the 0.015t greater than, again, because there was multiplication, the natural log of 1.26 plus the natural log of e to the 0.009t, okay? These are just going to be constants, okay? So nothing too alarming. Let's leave them the way we are now. But here we have the natural log of e, which is just going to leave us with 0.015t. Same goes for here. That's going to just leave us with 0.009t, okay? So actually, I'd like to isolate my variables. So I'm going to subtract 0.009t onto this side. And I'm also going to subtract the natural log of 1.01 onto this side, okay? So 0.015t minus 0.009t is going to get us 0.006t. And then over here we have the natural log of 1.26 minus the natural log of 1.01. Divide both sides by 0.006. Let me erase that. Type that into your calculator and you're going to find that t must be greater than 36.86 years. So about 37 years from now, India will be 37 years from 2000, India will be the most populous country